Hello everyone. Today we'd like to study a disk around the WTTS. Accretion of gas becomes weak and segregation of solid particles from gas starts, and we could discuss the growth process of solid particles in a disk. The model of a disk around the WTTS was developed by Hayashi, so sometimes we call it Hayashi models. We have several assumptions. First assumption is an axisymmetric disk. There is no special directions in a disk. If we consider the derivative with respect to theta, this becomes 0. Then optical thin disk assumptions, constant temperatures in z directions. No accretions, so this means radial velocity of gas becomes 0. No self-gravity of a disk. So we consider the mass of a protostar. It's much heavier than the mass of the disk. This is the fourth assumption. So we use these four assumptions to build a Hayashi model. Then we'd like to find out the temperature of a disk. So we consider energy released by a star is directly received by solid particles in a disk. Then the solid particles radiate the energy following the Stephan Boltzmann laws. Stephan Boltzmann law said the released energy from the surface of a solid particle is expressed by the sigma times the T to the fourth. T is the surface temperature of a solid particles. We use this to find out the temperature of a solid particle that is exactly equal to the temperature of a disk. So in practice 4.2, we'd like to find out the temperature distribution of a disk. The solid particles emit the received energy following the Stephan Boltzmann law. Compute the temperature of the solid particles. Assume the luminosity of the star is that of the sun, 3.9 times 10 to 26 watt. Star emit the light in all the directions uniformly. Radius is r. Then cross-section of the solid particles is obtained pi r squared. The distance from the star to the solid particle is r. The received energy from a protostar can be calculated. L is the total amount of energies emitted from a protostar. L is the luminosity is divided by the 4 pi r squared. 4 pi r squared you can consider spheres with a radius of the r. Then total area of a surface of a sphere is given by the 4 pi r squared. L divided by the area of a spheres. Then you need to multiply the pi r squared is the area of a solid particle. This is the received energies. Then emitted energies from the surface of a solid particle can be calculated using the Stephan Boltzmann laws, sigma T to the fourth. This is the emitted energy per unit areas. Unit multiply the surface area of a solid particle is a 4 pi r squared. Then received energies have to be balanced with the emitted energies. So this means T to the fourth is equal to the L over 16 pi sigma r squared. Then from this equation, if you substitute the luminosity of the suns and r is equal to 1 AU, then T can be calculated 280 kelvins. L substitute solar luminosity, power index 1 over 4, R over 1 AU minus 1 over 2. This is solar luminosity is 3.9 times 10 to 26 watt. So we could find out the temperature of a disk considering the energy balance of a solid particles. Then we discover the temperature distribution of a disk is given by this 280 kelvins at 1 AU. Temperature of a disk as a function of a distance from a protostars, and the unit is AU. This is 0. At 1 AU, 280 kelvins. This temperature is a decreasing function with distance. At 3 AUs, temperature dropped to the 160 Kelvin. This 160 Kelvin is about the sublimation temperatures. We call the snow lines. Beyond the snow lines, water becomes water ice. Inside of the snow lines, water turns to be the gas. So it changes the phase by crossing these snow lines. So if you consider the positions of each object in the solar system, in the Earth regions, temperature is 280 kelvins. Then water becomes a gas phase. In the position of the cities, temperature is 167 kelvins. So it's very close to the sublimation temperatures. In the locations of the Jupiter and the Saturn, temperature is lower than the sublimation temperatures, so we expect phase of water becomes ice. Then in practice, 4.3. Suppose we create a rocket and try to approach the sun as close as possible. How close can we approach the sun? The rocket is made of irons and the melting temperature of iron is about 1400 kelvins. So with this temperature low, then we substitute T equal 1400 equal 280 R over 1 AUs and then minus 1 over 2. So from this equation, you can easily calculate R corresponds to 0.04 AU. So if the rocket is approaching as close as this quantity of the 0.04 AUs, start melt. Then I'd like to find out the ratio of the solid to the gas. Beyond the snow lines, ice component of the H2O, CH4 and the NH3 becomes a solid because the sublimation temperatures of each component is higher than the temperature of the disk. And the metal and the rock also the solid phase. Rock is the main composition of our mantles. And the metal of the iron and nickel is the main component of a core of a planet. Inside of the snow lines, ice component becomes a gas phase. Solid component becomes a decreasing inside of the snow line. Then we'd like to find out the solid to the gas mass ratios. So major component of the gas phase is the hydrogen molecules and the heliums. Then inside of the snow lines, mass ratio becomes a 0.0034 and beyond the snow lines, mass ratio becomes about 1 over 100. Then we'd like to find out the total amount of solid particles in a disk. Surface density of solid at 1 AUs. Hayashi built a disk model using the present knowledge of planet at these times. Surface density of solid at 1 AU is obtained by grinding the present mass of the Earth down to dust and uniformly distributed around its orbit. Then surface density of the solid can be obtained. For example, at 1 AUs, present mass of the Earth is distributed in these regions. We can find out the surface density of solid particles. Beyond the snow lines, contribution of the ice enhance the surface density of solid particles. Then we'd like to find out the surface density of gas. Surface density of gas is obtained from the ratio of the solid to the gas is 100. Once we find the surface density of gas and solid particles, by integrating surface density over the total area of a disk, we could find the total mass of a disk. Then we assumed the size of the disk is 50 AUs. This is the outer edge of a disk. And the inner edge of the disk is 0.3 AUs. It's a 0.01 solar mass. This is the total mass of the Hayashi model. If we compare the total mass of the disk with the observational result given by the Beckwith et al. In 1990s, surprisingly, deviation from observation is not large. We could consider the Hayashi model might be a good model to consider the growth process of the solid particles. Okay, this is the end of the first lecture.